Hi everyone, welcome back. In this particular video, we're going to start talking about the aldol reaction. Now, this is a reaction of carbonyl compounds, which means it includes aldehydes and ketones, and specifically where at least one compound, and we'll look at the details, but we need an alpha hydrogen here, okay? This reaction can work under both acidic or basic conditions, okay? And depending on the reaction condition, it would involve the formation of either the enol or the enolate as a nucleophile. So if the reaction is proceeding under acidic conditions, then it involves the enol as a nucleophile. And if the reaction proceeds under basic conditions, then it involves an enolate as a nucleophile. Now, I've put a very generalized scheme for this reaction as to what happens in this reaction. And so what we're looking at here is one carbonyl compound. And notice I'm using Z here, and I've mentioned that Z can be an R group, an alkyl group, or some carbon-containing group, or a hydrogen. So if it is a carbon-containing group, then we're looking at a ketone here. But if it is a hydrogen, then we're looking at an aldehyde. But I've drawn the most simplest, the basic representation for a carbonyl compound which has an alpha hydrogen, or which has at least one alpha hydrogen. So notice there is an alpha hydrogen here. Okay, so this is alpha because this carbon is alpha. So we have one carbonyl compound and we have another carbonyl compound. And what happens in this reaction is under acidic or basic conditions, you make a bond between the carbonyl carbon and the, you make a bond between the alpha carbon of one carbonyl compound, so the compound which has an alpha hydrogen on it. You form a bond between the alpha carbon of this carbonyl compound and the carbonyl carbon of the second carbonyl compound. So that's what we're seeing in the product here. So if you compare the reactant to the product, what we have is we have the alpha carbon. So that's the alpha carbon here. And now the alpha carbon has a bond to the carbonyl carbon of the second carbonyl compound, or the other carbonyl compound. Now, in terms of an alpha beta nomenclature, this carbon now would now be a beta carbon, okay? Because starting from the carbonyl group, this is alpha and that's beta. So this compound here that we've made, these are in general called beta hydroxy carbonyl compounds. Okay, beta hydroxy carbonyl compounds. Now, if this Z is a hydrogen, then we can be specific and we call it a beta hydroxy aldehyde. Or if Z is a carbon containing group, then we can go specific and we can call it a beta hydroxy ketone. So it really depends on what Z is here, because we're just defining it very generally to say it is a beta hydroxy carbonyl compound. Okay, now under these reaction conditions, okay, again, if you have acidic and basic conditions, the beta hydroxy compound, under most general circumstances, when you heat it, if you're heating this reaction, what happens is the beta hydroxy carbonyl compound undergoes a dehydration. So it loses a molecule of water to give you this compound here, where there is a double bond between the alpha and the beta carbons. So if you look at it overall, starting from the beta hydroxy compound, we've lost one of the alpha hydrogens from this carbon, okay? And we've lost the hydroxyl group on the beta carbon. So that's why it's a loss of water. It's overall a dehydration. And this compound is an alpha beta. So because we get this double bond, this compound is called an alpha beta unsaturated carbonyl compound. Again, based on the nature of Z, we can go specific, and this compound can be called an alpha beta unsaturated aldehyde or an alpha beta unsaturated ketone. So that's the aldol reaction. Now, the aldol reaction happens in 2 steps. Okay, there are 2 steps to the reaction. The first step is where the reactants, that means the 2 carbonyl compounds, are converted into the beta hydroxy carbonyl compound. This first step of the reaction is called an aldol addition. Okay, this is an aldol addition. Now, I should also mention that this beta hydroxy carbonyl compound is also called an aldol compound, because if you look at it, if Z is a hydrogen, okay, if Z is a hydrogen, then it would have an aldehyde functional group and it has an alcohol functional group in it. So to represent those, it's called an aldol. Now, if Z is a carbon-containing group, you can call it a ketone. But the general name aldol is used to represent or to identify any compound that is a beta hydroxy carbonyl compound. Okay, so that's where the name aldol comes from. So the first part where you make this beta hydroxy compound, that's called an aldol addition reaction. When you go all the way to the alpha beta unsaturated compound, starting from your reactants, this reaction is called an aldol condensation reaction. Okay. Now, if you go from this second step to the alpha beta unsaturated compound, you can still call it a condensation because your aldol is undergoing a condensation step. So there's depends upon like what you're looking at. So if you're looking at a reaction where your starting materials end up as the alpha beta unsaturated compound, you can call it overall an aldol condensation. But if you have a case where it goes stepwise, then the first step would be an aldol addition, and then the step 2 would be the aldol condensation here. So that's also a condensation. And a condensation is generally reactions where you lose a small molecule like water or ammonia or something like that. Okay, so that's the aldol reaction. Now we can look at a specific example here. Okay, so that we're looking at some molecules here. So let's look at a specific example. And what we can consider is the reaction between, let's say, a simple aldehyde. So let's say we have acetaldehyde. That's one of the carbonyl compounds. And acetaldehyde is reacting with benzaldehyde, let's say. Okay, so acetaldehyde reacting with benzaldehyde, those are the 2 compounds. Now, there is a reason why I've chosen acetaldehyde and benzaldehyde, but those reasons would slowly reveal themselves as we go through the discussion. Okay, but if we react these, and it doesn't matter whether it's acidic or basic conditions, so either under acidic or basic conditions, we're going to get the aldol product, which would be C double bond O, and the alpha carbon here is going to be connected to the carbonyl carbon, and that would be a hydroxy group. So we have that with the hydroxy group here. So that's alpha, this is beta. And since this is benzaldehyde, on the beta carbon, you're going to have a benzene ring. Now, this beta carbon also has a hydrogen, and you can draw it out, but it's not required in the bond line representation. So this would be our aldol product. Okay, so notice now this is an actual aldol because there is an aldehyde functional group and there's an alcohol functional group. And when you heat this further, okay, upon heating it, this product is going to convert into the alpha beta unsaturated aldehyde. Okay, so that's alpha, this is beta, there's unsaturation or there's a double bond there. So that's your alpha beta unsaturated aldehyde. So that's the product from the reaction between acetaldehyde and benzaldehyde. Okay, so that's how you would write the products. But what we're going to do next is we're going to look at the mechanism of this reaction. And there are too many small things like details to remember. There are too many details to remember as we go through this mechanism. So what we're going to do is we're going to slowly work through the mechanism under both acidic and basic conditions and see how does this reaction work. How do the two carbonyl compounds first become a beta hydroxycarbonyl compound and then become the alpha beta unsaturated compound. So now we're going to look at the mechanism of an aldol reaction under acidic conditions. And for the purposes of mechanism, I'm choosing to work with acetaldehyde, which is the simplest aldehyde that contains an alpha carbon in it. And the reaction that we're looking at is sort of the dimerization here, okay? The reaction of one acetaldehyde with another one of itself. So we have two equivalents of acetaldehyde, and we'll see how that's converted into the beta hydroxyaldehyde compound and subsequently to the alpha beta unsaturated compound under acidic conditions. Now, one thing that I want to point out is that although for stoichiometric purposes, we show the two equivalents of acetaldehyde, you don't really need two equivalents of acetaldehyde here. Let's see why that's the case, okay? So if we think about mechanism here, so since we are under acidic conditions and we are doing a reaction that involves the alpha carbon, notice we are making a bond between the alpha carbon of one aldehyde with the carbonyl carbon of another aldehyde. So that means there should be a nucleophile, and the nucleophile under these acidic conditions is going to be the enol intermediate. That would be our nucleophile. So the first step in the mechanism is going to be the protonation of the aldehyde. So the aldehyde here is going to get protonated under acidic conditions to give us the protonated aldehyde, and we will get water along with it. But this reaction is going on under aqueous acidic conditions. So there is water, plenty of water, or there might be another solvent which can always act as a weak base and a weak nucleophile. So after the protonation event, what's going to happen is we're going to use water to deprotonate the alpha hydrogen. That's alpha, this is H alpha. So the alpha hydrogen gets deprotonated. The electrons from that bond come into the space between the carbonyl carbon and the alpha carbon, and simultaneously the double bond here gets pushed up. And so this would give us the enol. So we've done about 3 electron pushes here, but we're trying to make the enol here directly. Now you could work in 2 steps and make the enol in two steps and do resonance in between. But that's not required. We can show the formation of the enol directly. So we've made the enol. So now that we've made the enol, what's important to realize is that not all of this aldehyde is converted into the enol. This aldehyde form, this is the keto form of the compound, and we have the enol form. And at equilibrium, very little of the keto form is converted into the enol form for simple carbonyl compounds like this. And what that means is when you reach equilibrium for this keto-enol tautomerization, there is some enol, but there is a lot more of the keto form still present. So what the enol can do is it can do a nucleophilic attack on a second molecule of protonated aldehyde. Okay, so this species here that has not converted into the enol. So the enol can do a nucleophilic attack on this second molecule of the aldehyde. So that's very important to realize here. We have an equilibrium, and the enol that's formed, it goes and attacks another one of this protonated aldehyde molecules. Now, whenever we are going to show the attack of the enol, we're going to push electrons like this. We're going to start with the oxygen lone pair, bring it down to form a lone pair, and then we'll use the pi bond to go and attack the carbonyl carbon. Okay, and again, keep track of the alpha carbon. So that was our alpha carbon. So the alpha carbon is now attacking the carbonyl carbon. Simultaneously, the double bond here is going to open up. So what this is going to give us is we will get the beta hydroxy compound, but it's going to be protonated here. Okay, so we're going to have a positive charge on this oxygen because that's protonated already. Then we've got the alpha carbon here, single bond, and the alpha carbon has a bond to the other carbonyl carbon. On that carbon, we have a hydroxyl group, and there is a methyl group. There's also a hydrogen here, but I'm not showing it because we're working with bond line structure. So there is a hydrogen on this carbon, and that's our beta compound. Okay, so we've made the beta hydroxy compound, but we're not there yet. Okay, there's this final acid-base reaction or a deprotonation event that has to happen. So water molecule can go ahead and deprotonate that oxygen, the aldehyde oxygen, the carbonyl oxygen, and that's going to give us the beta hydroxy carbonyl compound. And plus, we've got hydronium ion. Okay, so that's how we make the beta, or that's how the beta hydroxy aldehyde is formed under acidic conditions. So that's our aldol product. Okay, this is our aldol product. So we've made, or we've formed the aldol product here. Now, under heating, okay, when you're heating this reaction mixture, the second step, the condensation, is much faster. Okay, it proceeds at a very appreciable rate. And so how do we get rid of that hydroxyl group and we get the double bond between the alpha and the beta carbon? What we are going to do is, since we need to remove a hydroxyl group here, what we can do is we can take the lone pair from the hydroxyl group and protonate it, because under acidic conditions, the way we remove a hydroxyl group is by first protonating it so that we can convert it into a good leaving group or a better leaving group. Okay, so another protonation of the hydroxyl group, and that would give us the protonated beta hydroxy compound, but now it's protonated at the hydroxyl group there. Here's our alpha carbon, that's our beta carbon. Okay, so it's protonated, and along with that, and along with it, we have water. Okay, and so what happens next is we have to get rid of that water molecule or leave that, but that process is assisted by the water, and what it does is it deprotonates another alpha hydrogen. Okay, so we started with a compound which had 3 alpha hydrogens here. We used one of the alpha hydrogens to make the enol. There were 2 additional alpha hydrogens left. So now, once this step is formed, what the water can do is it can go ahead and deprotonate one of these alpha hydrogens. And as that happens, the electrons from this bond, they go into the space between the alpha and the beta carbon, and the water molecule is eliminated. And this process is highly favorable in the forward direction, and it would give us the alpha beta unsaturated carbonyl compound. So alpha beta unsaturated aldehyde is formed, which is our condensation product. And along with that, we are going to get hydronium ion. So this process is only catalytic in acid. You don't need a lot of acid because the acid is regenerated. Now, as I mentioned, this alpha beta unsaturated aldehyde or any of these carbonyl compounds that are formed here, these are highly favored. Okay, the formation of this compound pushes the equilibrium towards the product. And that's because this compound here is stable due to conjugation. Okay, and conjugation, I think one of the easiest ways to identify when there is conjugation present in a molecule is to look for double bonds. Okay, so when you see 2 double bonds that are skipped by a single bond, then we can say that there is conjugation present in the molecule. Okay, so we have a double bond, single bond, double bond. Whenever you see that pattern, there is conjugation present in the molecule. Okay, and how conjugation, why does conjugation help here? Why does conjugation make this molecule stable? That's because when you have the alpha beta unsaturated carbonyl compound, because of conjugation, this is resonance stabilized because I can draw several resonance forms for this alpha beta unsaturated compound. So we can start by pushing the double bond up to the oxygen. That would give me the first resonance form where we have the O with a minus, double bond, methyl group, positive charge at that carbonyl carbon. So that's the first resonance form. And I can draw an additional resonance form where I take this pi bond and move it here. And that's going to give us O minus, double bond here, and a positive charge over there. So you notice how there are 3 resonance forms possible for this alpha beta unsaturated compound. So the presence of this extended resonance makes it very stable. Okay, and that's the driving force for this reaction to go forward. It just pushes the reaction forward. So that's how we get the alpha beta unsaturated carbonyl compound, or in this particular case, the aldehyde under these reaction conditions. Next, we're going to look at the mechanism of an aldol reaction under basic conditions. And to maintain some uniformity here, I'm using the same aldehyde, acetaldehyde, which would undergo an initial aldol addition to give the beta hydroxy aldol product, and then a condensation to give you the alpha beta unsaturated compound or the alpha beta unsaturated aldehyde. Notice that these 2 products are identical to the products that we obtained under acidic conditions. And again, the reaction overall needs 2 equivalents of the aldehyde because your product has 2 equivalents of the aldehyde combined in it. Okay, so let's look at the mechanism of this reaction, how it proceeds under basic conditions. So since we are operating under basic conditions here, the mechanism of this reaction is going to begin or start with an initial deprotonation of the alpha hydrogen. So under basic conditions in presence of a base, the base can deprotonate the alpha hydrogen. And when the base deprotonates the alpha hydrogen, the electrons in the bond between the alpha carbon and the alpha hydrogen go to the space between the alpha carbon and the carbonyl carbon, and the double bond here is pushed up to the oxygen. So this takes us to the enolate. Okay, so we've made the enolate here. So there's our enolate. Now, the enolate, recognize that it is a nucleophile again. Okay, it is another form of the enol, which is also nucleophilic from that alpha carbon. And again, similar to the formation of the enol, under these conditions, the keto form of the compound, which is the parent aldehyde, is the favored form. Okay, so that means at equilibrium, there is some enolate formed, but there is a lot more of the keto form present. Now, the extent to which the enolate is formed would depend on the strength of the base. Recollect from our previous discussion on the formation of enolates that if we use a strong base like sodium hydride or lithium diisopropyl amide, LDA, we can push this equilibrium to the enolate completely. We can convert the alpha, we can deprotonate the alpha hydrogen completely, quantitatively, to convert it into the enolate, but not so with an aldehyde. Okay, so at equilibrium, we will have some enolate present, but there will be a lot of the keto form still present. And so what can happen is the enolate, under these conditions, the enolate that's formed, it can react with another molecule of the aldehyde, the carbonyl compound. Okay, so I'm going to draw another molecule of the carbonyl compound. And that's why in this equation here, we've written two aldehydes, because we are using two aldehydes to form the product. And very similar to the mechanism with the enols, when we work with enolates, we're going to start by pushing that electron pair down to reform that double bond. And simultaneously, the pi bond here is going to open up and attack the carbonyl carbon, and the double bond is pushed up to the oxygen. So that means under these conditions, we will get double bond O. So we've got the carbonyl back here. There's our alpha carbon, and the alpha carbon is now connected to the carbonyl carbon, which is single bonded to an oxygen and has the methyl group on it. Again, notice there is a hydrogen present, but I'm not drawing it because it's the bond line structure. In fact, we didn't have to draw it here also, but I'm not going to draw it there. So we get this, the alkoxide form, okay? And this carbon now is the beta compound, or sorry, the beta carbon. And under these conditions, the alkoxide that's formed, this can get protonated from water, which is your solvent here, or any other protic solvent that may be used. And it would give us the beta hydroxy carbonyl compound. So we've got alpha, beta, and what we've made is the beta hydroxy aldehyde, which is our aldol compound. So that's the Aldol Addition product. And along with this, we have hydroxide present. This reaction is going on under basic conditions. So now, very similar to the acidic conditions, now the hydroxide is going to react again. So the hydroxide could deprotonate this beta hydroxy compound, And one of the possibilities is this hydroxyl hydrogen. Okay, that hydrogen is acidic because it's connected to the oxygen atom. But if it deprotonates that hydroxyl oxygen, then it takes us back to the previous step. So that's why we're drawing these as reversible steps. What's another possibility for a hydrogen that can be deprotonated? It is one of these alpha hydrogens, because remember, we still have two alpha hydrogens left in this compound. So what the base can do is it can deprotonate one of these alpha hydrogens. And when it deprotonates, the electrons from there goes to that alpha carbon. Okay. So it's going to bring us to the next intermediate here, where we have the aldehyde, beta hydroxy in the methyl group. And at this alpha carbon, we have a negative charge right now. Now, if you think about it, what we made here is basically an enolate. Okay, this is an enolate because this can do resonance, and the resonance form of this structure is going to be the enolate. So that's basically what it is. So these are both enolates. Okay, they're both different resonance forms of the enolate because we deprotonated the alpha hydrogen. So whenever you deprotonate the alpha hydrogen, what you make is the enolate. So this enolate is the resonance form, okay, of that enolate, which we did not show here. Okay, but that's the enolate. Now, once this enolate is formed, something very interesting happens. What the enolate can do is it can actually kick out that hydroxide as a leaving group. Okay, and there are two ways of showing it. You can show it from either resonance form. You can show this last step from either resonance form, because to make the alpha beta unsaturated aldehyde, what we need is a double bond between the alpha carbon and the beta carbon. That's what we need to get to that product. So essentially what happens is the negative charge here, it goes to the space between alpha and beta carbons, and simultaneously the hydroxide is kicked out. So you can show that loss of the hydroxide from this resonance form, okay, from this first resonance form, or you can show it from the second resonance form. And the way we show it here is we use the lone pair on the oxygen, bring it down. Simultaneously, one of the bonds from here goes to the space between alpha and beta, and the hydroxide gets kicked out. So doesn't matter how you show it, the electron push, but what it does is it gives you the alpha beta unsaturated carbonyl compounds. It gives you the alpha beta unsaturated aldehyde here. Okay, gives you the alpha beta unsaturated aldehyde, and along with it, you have hydroxide that's kicked out. Now, recognize that this is sort of a unique step based on whatever we've seen so far, because we are kicking out hydroxide. And what we know is that hydroxide is a bad leaving group. Okay, so why does this happen? Okay, that's again because of the stability of this compound. So the stability of this alpha beta unsaturated aldehyde compound that's formed, that drives this reaction forward. Okay, now the mechanism of this reaction, this particular step, this mechanism is called an E1CB mechanism. Okay, E1CB, where CB stands for conjugate base. Conjugate base. So we've seen E1 reactions before. These were discussed when we were dealing with alkyl halides, and alkyl halides make alkenes. And in that E1 reaction, our intermediate was a carbocation. Whereas in this particular reaction, our intermediate is a carbanion, okay, which is the conjugate base of this beta hydroxyaldehyde. So that's why it's called the E1CB mechanism, because there is an elimination happening here, but it involves the conjugate base of that beta hydroxy carbonyl compound. So that's the E1CB reaction here, or the step in this mechanism. But overall, that's the mechanism of base catalyzed aldol reaction. You can first make the aldol addition product under these conditions. And if you're heating the reaction overall, or if you're forcing it, you can go to the alpha beta unsaturated compound. The formation of this alpha beta unsaturated compound, that's the driving force for this second part of the reaction, where you make the Aldol condensation product. Now that we've discussed the aldol reaction under both acidic and basic conditions, and we've worked through the mechanism of the reaction, let's look at some problems. Let's try to see if we can put down the structures of the aldol addition product and the aldol condensation product for a given set of aldehyde or ketone when we have the reactant given. So, and I've chosen two different reactions here. One's under basic condition, one's under acidic conditions. But what's important to realize is the nature of the product, okay, the structure of the product does not differ whether the reaction's done under acidic conditions or basic conditions. That product still looks the same. Okay, so if you were to do this reaction under acidic conditions, you will still get the same products under those conditions. So with this aldehyde here, what's important to always recognize or identify for these reactions is your alpha carbon, okay, because that's what does the attack. Okay, so we have the carbon here, so this is our alpha carbon, okay, and this has a chain on it. So there's another substituent connected to the alpha carbon. But just to work through it, like mentally work through it, what we need to recognize is that when this compound reacts with the base, okay, in presence of base, this compound is going to make an enolate. So let's draw the structure of the enolate. What would that look like? Since we're under basic conditions, we should be drawing the enolate. So the enolate that we're going to make is going to look like this. Okay, that would be the structure of the enolate. Now, in case you're confused here, right? Let's say if it doesn't make sense, we can actually try pushing some electrons here. So that's our alpha hydrogen. Okay, so essentially the base deprotonates the alpha hydrogen, and the electrons in the bond between the alpha hydrogen and the alpha carbon go to the space between the alpha carbon and the carbonyl carbon, and the double bond gets pushed up. So that's how I get to the structure. Now, one thing to notice here is I am drawing this enolate in the E configuration. Okay, that's because we do have a double bond here, and the more stable alkene would be the E alkene in this case. So I'm not drawing the Z alkene. The Z alkene would be where the methyl group is pointing up. That would be the Z alkene, but we're drawing the E alkene over here. Okay. Now, subsequently, once this enolate forms, this enolate is going to attack the carbonyl group of another aldehyde, because again, recognize at equilibrium, you will have some enolate, but there will be a lot of the keto form still present. So we can show that by pushing those electrons down, and this is our alpha carbon. The double bond from here goes and attacks the carbonyl oxygen. So essentially, this is going to now give us, I'm going to flip around the molecule a little bit. This is going to give us HC double bond O. Here's our alpha carbon from this enolate. Okay, I basically flipped around the molecule a little bit. So we have the aldehyde, we have the alpha carbon. The alpha carbon is now connected to the carbonyl carbon that should have the O minus on it. And the carbon should also have an ethyl group to it. Okay, and the hydrogen is there. You could show it if necessary, or you could skip it. But what's important to realize is the alpha carbon here also had a methyl group to it. So we have to include that substituent here. So there's our methyl group on the alpha carbon. So that would be the compound, and then this compound with water is going to get converted into the beta hydroxy carbonyl compound. So that would be our aldol product. So I just worked through a quick mechanism to identify what the product is going to be here. Okay, so that's our aldol product. So I'm going to put that here now. So we have the aldehyde O, that's our alpha carbon, hydroxy group, and ethyl group with a methyl group. Now, if you look at it, what we essentially did is we connected the alpha carbon of one of the aldehydes with the carbonyl carbon of another aldehyde. That's what we're doing over here. So the alpha carbon is connected to the carbonyl carbon of the other aldehyde, and we have a hydroxyl in place of that carbonyl carbon. And then everything else is pretty much the same. And now once you've put down this beta hydroxy compound or the aldol compound, writing the alpha beta unsaturated compound is very easy, because all that we have to do is, if you have the alpha hydrogen here, you're removing this alpha hydrogen and you're removing that hydroxyl group to put the alpha beta unsaturated compound, or put the structure for that alpha beta unsaturated. So that's alpha, that's beta. I'm going to draw the ethyl group here and the methyl group here. Now, even when I draw this alpha beta unsaturated compound, what's important to recognize is this is still the E alkene that I'm drawing, because that's going to be the major product. Okay. Now, if you look at it overall, okay, to draw this alpha beta unsaturated compound, what we did is we took two aldehydes, because we are using the same aldehyde. We took two aldehydes, and the condensation product here is basically we removed the alpha hydrogens on one of these carbonyl compounds, the carbonyl oxygen on the other carbonyl compound, and we created a double bond between the alpha carbon here and the carbonyl carbon there. And we write a product that's of the E stereochemistry. Okay, that's the E product. So we just write that. So this is the E product that we get. That's essentially what we've written over there. Okay, so you're basically removing the two hydrogens, or removing two hydrogens. If there are more than two, you're still going to remove two. If there are three hydrogens, you still remove two. So you're removing two hydrogens from the alpha carbon and the carbonyl oxygen, and making a double bond between the alpha carbon and the carbonyl carbon of the other molecule, and you're removing a water molecule overall. That's how you put down the structure of your product there. That is the alpha beta unsaturated compound. So putting down the structure of the product itself is very easy here. Okay, let's look at the second molecule or the second example here. And what we'll do is we'll try to first just do it intuitively and then also work through a mechanism to look at the details. So we are going to work with two equivalents of this compound. So we have a ketone now. Okay, so we're working with a ketone this time. So we have a ketone, one ketone, and then a second ketone. So when we do the aldol addition, like we said, we're going to do is we're going to make a bond between the alpha carbon of one of these compounds and the carbonyl compound, the carbonyl carbon of the other molecule, and convert this double bond into a single bond or a hydroxyl group over there. So the addition product here is going to be alpha carbon of this molecule is connected to the carbonyl carbon of the other molecule, but it's now a hydroxyl group. So that's where the hydroxyl group is. And on the carbonyl carbon of the second molecule, we have a third butyl group and we have a methyl group. So that's the structure of your beta hydroxy compound. Okay. And then when you heat it, so that's your beta hydroxy compound. And when you heat it, you're going to make the alpha beta unsaturated carbonyl compound, which is going to be double bond alpha beta. And since we have to write the E alkene here, we're going to write the T butyl over there and the methyl group over there so that we write the E alkene. Okay. And if you look at it again, overall, what we did is to put the condensation product down, we removed two hydrogens from this alpha carbon, we removed that oxygen and made a double bond between them. Okay, this alpha carbon had 3 hydrogens on it, so it still has 1 hydrogen left. So overall, there's just loss of a water molecule here. Okay, so those are the products. Now, in terms of a mechanism, what would happen here is that under acidic conditions, we're going to make an enol. Okay, we're going to make an enol. So the enol that we're going to make here is going to look like this. It will have a hydroxyl group and a double bond between the carbonyl carbon and the alpha carbon. That's our enol. And then this enol is going to attack or react with another one of the protonated ketones. So the oxygen brings its lone pair down, double bond here goes and attacks that carbon, and the double bond opens up. So that's going to give us the third butyl, C double bond O, H, positive charge, and the alpha carbon is connected to the carbonyl carbon, which is now a hydroxyl group, and that carbon has a third butyl group connected to it and a methyl group connected to it. This is your beta carbon. And so if you look at it, this is just a deprotonation away from your alpha beta hydroxy compound. Okay, so that's the alpha beta hydroxy, beta hydroxy ketone, and this is our alpha beta unsaturated ketone. Okay, so that's how we get the two products from this reaction. I hope you like this discussion of the base catalyzed and the acid catalyzed aldol reactions and the salt examples that we worked out.